Hello everyone, welcome to the course on signal processing. This is lecture 4 and in this lecture we will see the causality and the stability. So, the causality and the stability of a system, of a LTI system is described by, so first we will see that how we can check the causality. If the present output at any time depending upon the present and or past values of input, then it is said to be a causal system. Stability means if the bounded input results in the bounded output, means let us say the input is finite and it result in the output also to be a finite quantity, then it is said to be a stable system. So, we are combining now. So, first of all, what is causal? So, a system is said to be causal if the present output depends on the present or the past values of input, and if the system is depending upon any future value of the input signal, then the system is said to be non-causals. And we can say that the causal systems are realizable, whereas non-causal systems are not physically realizable. And we have the condition that to check the causality is when a system is LTI, then we can say the impulse response Hn is supposed to be 0 for all n less than 0, means for all negative values of n the impulse response value is 0. That signifies that the system is causal. Also we can say that a causal system is a non-anticipatory system, whereas a non-causal, as I have already told you, that it depends on the future value of input, means if present output is depending upon any future value of input, then we can say the system is said to be non-causals. And generally in signal processing we can say that non-causal systems are not physically realizable. So, we will see some cases, some questions, how can we identify that the system, corresponding system is causal or not. So, we have the first question, show that the relaxed LTI system is causal if Hn equals to 0 for all n less than 0. So, how we can prove this property? Basically, we are aware that for a LTI system, if Xn is the input, Hn is the impulse response, then the output Yn can be given as x of n convolution with h of n. So, these are the basic concept of signal system, we are already aware of this. So, Yn equals to xn convolution with hn. Now, we are going to utilize this relationship to prove this particular condition, that impulse response Hn is 0 for all negative values of n, which is n less than 0. So, this convolution can be written as, further written as, that summation k equals to minus infinite to n hk and further x of n minus k. In our next lecture also we will see how the discrete convolution will take place analytically also and graphically also. So, we are just further breaking the summation part here. So, I am taking summation from minus infinite to minus 1 and further summation will be k equal to 0 to n. And further let me expand this part left hand side. So, some k equals to minus 1 and x of n plus 1. Similarly, here if I am expanding this, h of 0 x of n plus h of 1 x of n minus 1 plus h of 2 x of n minus 2 and so on. So, there are some terms this side and some terms to the left this side. So, for a discrete LTI system to be causal, means now we will go to the condition, go to the definition of a causal, that present output depend upon the present value of input. So, if we want this system to be causal, that means the output Yn must not depend upon x of n plus 1, means if this expression is independent of this. So, what we can say that if h of n equal to 0 for all negative values of n, so we just eliminate these terms, these all left hand side terms will be eliminated by putting this particular condition. So, we are left with these right hand terms, and here we can clearly see that it is depending upon xn, x of n minus 1, x of n minus 2, n minus 3 and so on. So, the condition here derived is that if Hn equal to 0 for all the negative values of n, so this system is said to be a causal, and this is the we can say a small derivation. Now, we have a next question. Now, we need to check that the system here described by the following equation is causal or not. So, we have 2-3 cases. These cases are quite easy. Let us see this first case. Yn equals to 3 times of x n minus 2 plus 3 times of x n plus 2. Clearly, the output yn, if I am putting n equal to 0, so what we can say, at n equal to 0, the input will be taken as x of minus 2 and x of 2. So, corresponding to y of 0, what we can say, x of 2 is a future value, it is a future value of input. So, whenever as per the definition the present output depending upon the future value of input, then the system is said to be non-causal. So, here we can say the system is said to be non-causal. Let us see the second case here, that yn equals to x of n minus 1 plus some constant a multiplied by x of n minus 2. So, clearly what we can say in this expression here, that for all values of n, let us say we will put n equal to 0. So, we are getting x of minus 1 and x of minus 2. So, naturally it is a past value. So, we can say it is causal. Let us check some negative values also. Y of minus 1 will be x of minus 2. So, minus 1 and minus 2. So, with reference to minus 1, minus 2 is a past value, right. So, what we can say, that the output is always depending upon the past value of inputs. So, that is why the system is said to be a causal system. Next, yn equals to x of minus n, which is a quite important or interesting case. Let us put y of 1. So, y of 1, naturally it is x of minus 1. So, by seeing this particular expression, we can say the output, present output is depending upon the past value of input. So, it may be causal, but once we are putting a condition which is y of minus 1, so it will give us x of plus 1. Now, we can clearly see that with respect to minus 1, plus 1 is a future value. So, the present output, which is y of minus 1, is depending upon the future value of input, which is x of plus 1. So, we can say that the system here is definitely a non-causal. So, keep this in small thing in mind, that always we need to check some positive values of n, some negative values of n at, and also at n equal to 0. So, by checking these 3 cases, we can say that we are able to predict whether the system is causal or non-causal. So, next we have the equation, difference equation, which relates input and output. So, the question says that the discrete time system is represented by the following difference equation, in which xn is input and yn is output. So, we need to check whether the system is linear or non-linear, shift variant or invariant, and also for causal and non-causal, means we need to check all the 3 properties of system. So, first we are starting with the linearity. So, in the last lectures we have seen that what is a small condition to check the linearity of the system. So, a system is said to be linear if it follows principle of superposition. Now, what is principle of superposition? It says that principle of superposition is additivity and homogeneity. So, additivity and homogeneity. Homogeneity, we are aware that we are multiplying by a factor of a and b here, and additivity means after this multiplying by a and b, and we can just perform the addition. So, what we are getting here this side. So, we are going to check this particular condition for the linearity. So, how this condition works, what we will consider here is, let us say if x1 n is the input, so it will give rise to the output which is y1 n. Similarly, if x2 n is the input, it will give rise to y2 n. So, let us see both the cases when we are applying x1 n as input and y1 and x2 n as input. So, in the first equation, when we are considering x1 n as the input, so we are getting the first equation which is y1 n plus 3 times of y1 square n minus 1 minus of n x1 n plus 4 x1 n minus 1 minus 2 x1 n plus 1. Here it is n plus 1. So, this is the first equation. Now, when the input is x2, so definitely the output will be y2. So, we are getting a next equation here when the input is x2. Now, we will multiply both these equations first and second by a and b constants respectively. So, we are getting an equation here which is a multiplied by y1 n, and here we are getting b multiplied by y2 n, and we are just performing the addition. So, what we are getting here in the left hand side, we are getting a times of y1 n plus b times of y2 n. Now, to the right, if you are multiplying this by a and this by b, and we are taking common. So, let's take common in the next step. So, we are getting 3a y1 square plus 3b y2 square y of n minus 1. Similarly, we are getting these terms also, and if we are taking some common from this particular third equation, so we are getting this fourth equation. So, this is first part. Now, we have written basically the RHS side, right hand side we have written. Now, we have to verify whether this right hand side condition is equal to the left hand side or not. So, we can clearly see here that we are having a square y square. So, if we are putting y1 n plus y2 n, so we are getting y1 square plus y2 square plus 2 times of something like this. So, which will be definitely not equal to this particular equation number 4. So, what we can say that the superposition theorem is not verified here, and the system is said to be a non-linear system. So, this is a very important condition to verify. Now, we will check for whether system is variant or system is invariant. Now, how can we verify? There is a small condition we have seen in the last lecture, that first of all we are shifting in the signal, input signal, and we are applying a system. We will see the output, and first of all we are applying a system and then we are performing a shifting. So, that is called, if both the equations are same, we can say it is shift invariant. So, the definition for shift invariant is, if a time shift in the input signal results in an identical time shift in the output signal, then the system is said to be shift invariant, and if there is some other shifting in the signal, output signal, then the system is shift variant. So, let us write down this right hand side first. So, we will perform the delay in the input signal x of n minus k, and we will apply the system onto that input. So, we are getting 3 times of y square n minus k, and in whole equation we are getting n minus k, and we are applying the system. This is quite important point. We are not replacing n equal to n minus k. First of all, we are just delaying the input signal x of n minus k, and we are applying the system over here. So, we are getting an equation which is, let us say, equation number 1. Now, what about this y of n minus k? Means in our previous equation, instead of n, we are replacing n minus k. So, what we are getting here, instead of this n, we are getting n minus k this side. So, we can see apart from this all other terms are same except this middle term. So, here we have n, here we have n minus k. So, we can say that both this left hand side and the right hand side equation, they are not equal. If they are not equal, then what we can say? The system is said to be shift variant. It is not a LTI system. It is a nonlinear as well as shift variant system. Now, the next step is to check the causality of the system. So, clearly the causality is very easy. We can see here that the present output yn is depending upon yn minus 1, which is a past value. Here also xn, which is the present value of input, x of n minus 1, which is a past value of input, and this is x of n plus 1, which is definitely a future value of input. So, as per the definition of the causality, if the present output depends on a future input samples x of n plus 1, then the system is said to be a non-causal. So, in this particular case, we have verified all the properties here: causality, shift invariance and the linearity. Now, we will consider the second case. Again we need to verify the linearity, shift invariant and the causality. So, first, if x1n is the input, so definitely it will give rise to y1n. So, we are getting an equation which is equation number 1. Similarly, when we have input is x2, naturally it will give rise to y2 here, and we are getting equation which is equation number 2. Now, we are multiplying equation number 1 by A and equation number 2 by B, and we just perform the addition of the equation. So, what we are getting here is A multiplied by y1n, B multiplied by y2n to the left, plus A multiplied by these whole factors, similarly plus B multiplied by these whole factors, and we will perform the addition. So, we are getting here equation number 3. This equation number 3. Now, what I can say that we are getting x1, we are putting x1n plus x2n, and definitely it will give rise to some output which is let us say y3. So, now instead of x1n plus x2n, we will put this instead of xn in the above equation, and again definitely will give rise to y1n and y2n. So, we can say that equation number 4 will be definitely equal to the next equation which we can produce by putting this whole factor x1n plus x2n instead of xn. So, the equation number 4 will be equal, and we can say the superposition theorem is verified. Once the superposition theorem is verified, we can make a comment that the system is linear. Now, we will check the shift invariance. So, definitely we will again follow the same property. First of all, we will shift the input signal x of n minus k, and we will apply the system onto that. So, by applying this system, we are getting equation number 1, which is x of n minus k plus 1 minus of 3x n minus k plus x of n minus k minus 1. This is equation number 1. Now, in the equation, last equation, instead of n, we will put n minus k. So, we are getting y of n minus k, x of n minus k plus 1. Also, here we can write x of n minus k, and here also x of n minus k. So, by seeing this equation number 1 and equation number 2, both the equations are identical. Once these equations are identical, we can say that the system is said to be time invariant. So, the system is linear also, the system is time invariant also. Now, we will go for the causality. So, by seeing this difference equation and the first term yn equals to x of n plus 1. So, we are already aware that when n equal to 0, the input will be x of 1, right. So, x of 1 will be definitely a future value. So, as per the definition of causality, we can say that the present output is depending upon the future value of the input. So, that is why the system is said to be non-causal. We can clearly see. So, this was the second case. Now, we will check the stability, because stability plays a very important role in the digital signal processing, because if the system is unstable, then we can say we are not going to realize those type of systems. So, generally we realize those systems which are said to be stable. So, as per the definition of stability, the transfer function of the discrete time system is a rational function. Definitely we are into the discrete domain. So, we are not having the S, we are having a Z transform with real coefficients. So, for what we can say, for a causal filters, the degree of the numerator, very important point, the degree of the numerator polynomial is equal to or less than that of the denominator polynomial. This is again an important point. And also by seeing the transfer function Hz or the system function Hz, what we can say, that if the poles of Hz lies inside the unit circle, then we can say that the system is said to be stable. If the poles are lying onto the unit circle or outside the unit circle, definitely we can say that the system is unstable, and once the system is unstable, definitely we are not going to utilize those, or neither we are going to realize those type of systems. So, let me discuss one small concept. This is, let us say, S plane, this is Z plane, complex Z plane, this is S plane, we are having sigma and here we are having j omega. So, what we are aware here is that the right side RHS is mapped outside, the j omega axis is mapped onto the unit circle, and whatever the points are in the left hand side, then we are said they are inside the unit circle. So, as per the Laplace transform also, we can say that if the poles are lying in the left hand side of S plane, the system is stable. If they are in the j omega axis or right hand side, we can say the system is unstable. So, similar concept is applied to the Z domain also. So, for the necessary and the sufficient condition for a DSP system to be stable is that all the poles of the transfer function Hz must lies inside the unity circle. So, this is an important condition. Next, we have the impulse response. We need to check, we have the difference equation available and we need to check whether the system is causal or not. Again, yn minus y of n minus 1 equals to xn plus x of n minus 1. So, first of all we are going to calculate the impulse response. So, what is impulse response? When xn is a impulse signal, so definitely the response of the system is said to be impulse response. So, by applying Z transform, we are getting Hz, and by taking the inverse Laplace transform of this, we are getting Hn equals to un plus u of n minus 1. So, clearly we can check the stability also depending upon the inputs. So, we have two inputs available and we need to check that for both the inputs whether system is stable or not. So, we can check by this particular equation, that yz equals to hz multiplied by xz. So, if we will compute that where are the poles of yz lying, if they are lying inside or outside, definitely we can make a comment. So, by seeing here that the poles are lying on z equals to 1, which is a complex circle. So, the system is unstable. We can say system is unstable. And also for the second case, again we will calculate the Hz and will try to find will calculate Yz and will try to find out the locations of the poles. By seeing this, we can say the poles is lying on z equal to 1, which is the unity circle, and one pole is lying inside the unity circle. So, depending upon this, the system is said to be unstable. So, BIBO means when the input is bounded, so the output has to be bounded. So, for this we have derived a small condition that if Hn equals to 0 for all less than 0, we have already derived for causality, and for a BIBO stability, the impulse response must be absolutely summable. So, this condition has to be verified for the stability. Lastly, we have this small question. We need to check the stability of the system. Yn we have. So, first we will need to identify what is the impulse response, and by calculating the impulse response, we will check whether the impulse response is absolutely summable or not. If it is summable, then definitely it is stable. So, here we can say that the system impulse response is basically a finite quantity. If it is a finite quantity, so it is a stable. So, these are the references. Thank you.